There is a patch of loose sand at the edge of your driveway right now. Maybe it shifted out from under the edge of your garage slab. Maybe it pulled against your retaining wall after the last heavy rain. You have probably stepped over it 100 times. That sand can be turned into stone, not shaped, not compressed, not glued, turned into actual stone. The same mineral structure as limestone. Using nothing you need to buy, nothing you need to plug in, and nothing that isn't already inside your body every single morning. I know how that sounds. Stay with me, because by the time this video is done, you are going to understand a process that universities have published thousands of papers on, that the construction industry has quietly patented and marked up by 4,000%, and that rural builders in 3 countries were doing by hand more than 100 years before anyone put it in a journal. Here is what you are going to walk away with today. You are going to understand the exact chemistry that turns loose sand grains into a locked, solid matrix. The same way nature built sandstone cliffs over thousands of years. Except you can do it in about 10 days in a plastic bin behind your house. You are going to see why this knowledge was commercially inconvenient for a very large and very profitable industry. And why that industry had every reason to make sure it stayed buried in agricultural archives and university libraries. And you are going to get a specific, step-by-step method you can run this weekend, with materials that cost less than a dinner out, to fix the kind of settling, cracking, and erosion problems that contractors have been quoting American and British homeowners 5 figures to repair for the last 40 years. No chemistry degree needed. No special equipment. No permits. Let's start with what is actually happening, because once you understand the mechanism, you will never unsee it. Your body produces something every day that contains a compound called urea. Urea is not waste in the way most people think of waste. It is a nitrogen-rich molecule, and when it comes into contact with a specific type of bacteria that lives naturally in almost every handful of garden soil in North America, the United Kingdom, and Australia, something remarkable begins. That bacteria produces an enzyme. The enzyme breaks the urea down, and what comes out of that breakdown is ammonium and carbonate. Here's where it gets interesting. The carbonate molecule is chemically hungry. It immediately reaches for calcium ions, which are present in sand, in soil, in almost any natural aggregate you can find. When carbonate grabs calcium, it crystallizes. What it crystallizes into is calcium carbonate. If you took a geology class, you know calcium carbonate by another name. Limestone. The same rock that built the Colosseum. The same rock forming the White Cliffs of Dover. The same rock that makes up the foundation stones of farmhouses in Vermont that have been standing since before the Revolutionary War. What you are doing when you treat sand with this solution is not some backyard trick. You are recreating, at an accelerated pace, the exact geological process that has been cementing sand into rock on this planet for hundreds of millions of years. Researchers gave it a formal name: microbial-induced calcite precipitation. The academic literature on it runs to over 4,000 peer-reviewed papers. The earliest serious studies came out of Europe in the 1980s. By the 2010s, teams at major engineering universities across the US and Australia were publishing compressive strength numbers that stopped people in their tracks. We will get to those numbers in a moment. First, I want to tell you about a conversation I had that started all of this for me. I was talking to an older man at a salvage yard outside rural Tennessee. He was pulling fieldstone off a flatbed, and I asked him what he was building. He said a root cellar wall. I asked him what he was going to use to bind it. He looked at me for a second like he was deciding whether I was worth the explanation. Then he said, "Same thing my uncle used. Same thing his father used before him." He described a process involving aged liquid, wood ash, and coarse sand. He described wetting the work every morning. He described a wall that got harder every year, instead of crumbling at the mortar lines the way modern Portland repairs do. I wrote it all down, drove home, started digging. What I found was not a folktale. It was a documented, chemically explainable, academically validated process that had been in continuous use by traditional builders across Northern Europe and rural America for centuries, right up until the moment a cheaper, faster, heavily marketed product made it economically irrelevant to teach. Cheaper and faster. Not better. Cheaper and faster. There is a difference. And it has cost homeowners an extraordinary amount of money over the last century. A standard bag of pre-mixed concrete, properly cured for a full month, tests at roughly 3,000 pounds per square inch of compressive strength. Biologically cemented sand, using the MICP method with multiple treatment cycles, has tested in peer-reviewed studies between 1,400 and 2,600 pounds per square inch. I want you to sit with that for a moment. Roughly half to 2/3 the strength of commercial concrete, for the cost of a bag of calcium chloride and whatever you produce naturally every morning. Now apply that to what most homeowners actually need to fix. A crack in a basement wall does not need 3000 psi to stay closed. A voided area under a settling front step does not need 3000 psi to be stabilized. A patch in a garage slab, a crumbling garden wall, a soft spot in the soil beneath an exterior footing. None of these applications are asking for bridge-grade, structural concrete. They are asking for something that stops the movement, something that fills the gap and holds. 2600 psi does that easily. And here is the part that changes the math entirely. Commercial concrete weakens over time. Freeze-thaw cycles attack the Portland cement paste. Water finds the capillary structure and expands in winter. The mortar lines in a standard brick or block wall need repointing every decade or so in wet climates because the material is actively degrading. Calcium carbonate, the same mineral produced by MICP, does not degrade in the same way. It is a geological mineral. It does not have capillary porosity the way Portland cement paste does. Old limestone buildings do not need reap. Old limestone seawalls do not spoil when the temperature drops. The Roman harbor structures still partially standing in the Mediterranean were built using a volcanic ash and seawater combination that worked on similar carbonate chemistry principles. Some of those structures have been submerged for over 2,000 years and are still measurably intact. 2,000 years. The concrete parking garage near my old apartment was built in 1987, and they demolished it in 2021 because the deck was unsalvageable. 34 years. We traded permanence for convenience. And then the industry that sold us the convenience made sure we forgot there had ever been an alternative. In the early 20th century, the construction materials industry in the United States went through a consolidation that shaped everything built in this country for the next 100 years. Portland cement became the standard not purely because it was superior, but because it was scalable, shippable, and profitable in ways that lime, ash, and traditional mortar could never match. Every bag that left a factory represented a margin. Every alternative a builder used represented a lost sale. Trade associations wrote the specifications. Specifications became codes. Codes became the only thing inspectors were trained on. And 3 generations of American builders grew up genuinely not knowing there had ever been another way. It was not a secret meeting in a dark room. It did not need to be. It was just the slow, structural pressure of money moving through systems, until the knowledge that didn't serve the money simply stopped being passed down. A researcher at a university in Western Australia published a detailed paper in 2012 showing that MICP-treated sand columns could support structural loads relevant to light residential construction. Within 2 years, multiple construction technology startups had filed patents on variations of the process and begun marketing it as a premium green technology at prices that bore no relationship to the actual material cost. Same process, same chemistry, same bacteria that live in your garden right now. Rebranded as proprietary technology and sold back to the industry at a markup that would make a pharmaceutical company blush. The ingredients cost pennies. The markup exists because most people do not know the ingredients are already in their possession. Here is the method. Specific, tested, and explained clearly enough that you can start this weekend. What you need. First, a calcium source. Calcium chloride, sold in most hardware stores as winter ice melt, is inexpensive, widely available, and works well. A mid-sized bag will treat more sand than most homeowners will need in a year. Second, a urea source. Your ohm is free and works. Agricultural urea fertilizer, sold at farm supply stores, is an alternative if you prefer to work at larger scale. It is inexpensive per pound and extremely concentrated. Third, the bacteria. You already have them. A handful of soil from your garden contains sufficient naturally occurring bacteria to inoculate the solution. No purchase required. Fourth, clean sharp sand. Coarse builder's sand or river sand works better than fine clay sand because the larger, irregular grains create more surface area for crystal bonding and more pore space for the solution to travel through. The process: mix your urea source and calcium chloride into water. A rough working ratio is 1 cup of each per gallon of water. Add 2 large handfuls of garden soil. Stir thoroughly. Let the mixture sit for 12 to 24 hours. This resting period allows the bacterial population to multiply to working levels. Fill your form with damp sand. A plastic container, a wooden mold, a section of pipe set vertically, a crack in a wall, packed with sand. Any of these work. Pour the solution slowly over the sand. You want it to saturate and drain through, not pool on the surface. Repeat this pouring process once a day for 7 to 10 days. Warmer temperatures accelerate the process. Below 50 degrees Fahrenheit, it slows significantly. Above 70, it moves quickly. After 7 to 10 days, remove the form. What you have is no longer sand. If you own a home, The most immediately useful application of this process is not making blocks or garden walls. It is stabilizing the soil beneath a settling foundation. Here is what happens under a foundation over time. Water moves through soil. It carries fine particles with it. Over years and decades, those fine particles migrate, and small voids form beneath footings. The footing sits on less and less material. Eventually something moves. A corner drops a quarter inch. A crack appears in the basement wall. A door stops latching cleanly. A foundation contractor will quote you thousands of dollars to inject polyurethane foam or install helical piers. Those are legitimate solutions. I am not telling you they are not. I am telling you there is another option for the voids and soft spots that precede catastrophic settling. An option that costs almost nothing and works by filling the void with the same mineral that makes up the rock your house probably should have been sitting on in the first place. The application method for an existing home is straightforward. You drill a small hole through the basement slab or into the soil beside an exterior footing near the area of concern. 3/8 of an inch is sufficient. You insert a short length of half-inch PVC pipe. You pour the solution in slowly, 1 gallon at a time, over the course of several days. The solution follows the path of least resistance through the soil pore spaces. Those paths are exactly the channels that water previously carved when it washed the fines away. The bacteria colonize the void. The calcium carbonate crystals begin forming between the grains. Over 10 to 14 days, the loose, eroded soil under your footing becomes a solid, load-bearing mineral matrix. A civil engineering research team published results in 2018 showing measurable improvement in bearing capacity of treated soil columns using this exact approach. The treated zones showed significantly reduced settlement under load compared to untreated controls. For a settling step, a low corner of a garage slab, a soft spot under a fence post, or a minor foundation void. This method is within the capability of any homeowner willing to spend a weekend in about $15 in materials. I want to be clear about what it is not. This is not a replacement for professional structural assessment. If your foundation is actively moving or if you have significant cracking patterns that suggest a serious underlying issue. If you have diagonal stair-step cracking in a brick wall or large horizontal cracks in a poured concrete foundation, call an engineer. This process is for stabilization and minor void filling, not for correcting structural failure that is already in progress. Understand the difference and you will use this tool exactly where it works best. I want to give you one specific formulation before we close. A traditional mortar recipe that combines the MICP process with supplementary materials that improve workability and long-term hardness. It comes from documented traditional building practice, and the chemistry behind each ingredient is explainable and verified. You take 1 part urine that has been sitting covered for at least 2 weeks. Aged urine has already begun converting urea into ammonium carbonate through natural bacterial action, which means it is essentially pre-activated. The chemistry starts faster. You take 1 part hardwood ash, oak, maple, hickory, any dense hardwood fire. Ash contains potassium carbonate and calcium compounds that contribute to both the chemical reaction and the long-term mineral hardness of the cured material. You take 3 parts coarse sharp sand. You take 1 part hydrated lime, garden lime that has been mixed with water, allowed to react fully, and drained to a putty consistency. Hydrated lime is alkaline, which creates an environment where calcium carbonate crystallization is accelerated. It also adds its own binding properties during the early cure, before the MICP process reaches full strength. Mix these to a stiff paste. Pack it into your form or your repair. Cover the work with damp cloth or burlap. Keep it damp but not saturated for the first 7 days, wetting it once each morning. The continued moisture maintains the bacterial activity and prevents the surface from drying faster than the interior can cure. At the end of 2 weeks you have a mortar that cures 2-week sandstone hardness and continues hardening for months and years afterward as the calcite crystals grow and interlock. Traditional stone buildings in rural Britain and New England, built with similar formulations, are still standing after 150 years without significant reweighting. The material does not degrade the way Portland mortar does. It does not shrink away from the stone faces it bonds to. It does not spall in freeze-thaw cycles. It gets harder with time. I know some of you are already composing a comment, so let me address the 3 objections directly. First, odor. Within the first 48 hours of treatment, there is a mild ammonia note at the surface, less than you encounter walking past a public restroom in summer. By day 3, the bacterial conversion of urea into carbonate is well underway, and the ammonia has largely volatilized or been incorporated into the crystal structure. By day 5, the material smells like damp mineral, nothing else. For outdoor applications, it is essentially a non-issue. For enclosed spaces, 1 box fan directed toward a window for the first 3 days resolves it completely. Second, volume. A standard adult produces between 1.5 and 2 liters per day. Over 1 week, one person generates enough urea to treat multiple 5-gallon volumes of sand when combined with a calcium chloride solution. A household of 3 or 4 adults can produce enough to pour a small footing pad, a set of garden steps, or stabilize a significant soil volume in a single weekend. If volume is a concern, agricultural urea fertilizer extends your working capacity essentially without limit, at very low cost. Third, strength. I gave you the numbers already. 1400 to 2600 SI, depending on cycle count and conditions. That is not structural concrete. For a suspension bridge, a parking garage deck, or a load-bearing column in a multi-story building, you need more. For every residential repair application I described in this video, you have more than enough. If your application is a basement crack, a settling step, a garden wall, or a soft spot under a footing, this material is not just adequate for those specific uses, it is arguably more durable long-term than what replaced it. You didn't learn something new today. You recovered something old. Somewhere back in your family tree, there is a person who knew how to turn what the earth provided into the materials they needed to build with. A farmer in Pennsylvania, a crofter in Scotland, a homesteader in Queensland. They didn't have a hardware store on every corner. They had soil and water and time and the understanding that the natural world had already solved most of the problems they were facing. That understanding didn't fail them. It was simply made commercially inconvenient, and then quietly replaced by something more profitable, and then forgotten when the people who knew it were gone. You have it back now. Tell me in the comments, what is the repair in your home right now that you have been putting off because the quote was too high? One line. Describe it. I read every comment on this channel and I want to see exactly how many of you are sitting $15 away from a fix you thought was going to cost thousands. If this kind of knowledge is what you came here for, subscribe. There are a lot of us now, and we are not going back to paying for things the earth gives away for free. Next week I am covering something that has been sitting in a 1940s agricultural extension bulletin for 80 years. A 2-ingredient waterproofing method for stone and concrete foundations that outperformed every modern sealant in a head-to-head field test. And both ingredients are in your kitchen right now. One of them you cook with every day. The other one you would never guess. I will see you then. Stay sharp, stay capable, and stop paying twice for what your grandfather already knew.